In the next two videos, we're going to look at how to improve instruction scheduling using static techniques. So in other words, we're going to pretend that we are a compiler and that we try to look at this sequence of instructions and make them run better. We are going to look at an architecture with some specific restrictions from a performance point of view. So more specifically, the restrictions are that from the time we finish one ALU operation until the following ALU operation can use our input, there has to be a latency of 3 cycles. From the time we produce a floating point result from the ALU until we can do a stored data out to the memory, there has to be a latency of 2 cycles. And from the time we do a load double until the time we do a floating point ALU operation is a latency of 1 cycle. So the latency number here is the number of cycles between the two adjacent instructions of these two types. Furthermore, this architecture is supporting delayed branches. That's what we talked about in the last video. So there's going to be 1 branch delay slots after each branch in this architecture, and we try to fill that with good architecture. So once more, the restrictions here is from output of the ALU to input to the ALU, from output to the ALU to input of stored data, and from stored double, from load double to floating point ALU. And here are the numbers. You may want to write down these numbers on a piece of paper so you can remember this. So you can ask yourself, we already saw this trick called forwarding and bypassing in an architecture. And so from an instruction that produces a result until that result can be used, it was actually a latency of 0 cycles. So what is this? If it's so easy to get, reduce that latency to 0 cycle, why do we study an architecture where there is a restriction on how quickly you can produce the result? Of course, there are different trade-offs. There could be architectures that don't have these feedbacks, but in this situation, we are looking at an architecture executing floating point instructions, and it's not very uncommon that floating point instruction takes more than 1 cycle in the execute stage. These are still a pipeline implementation, so the very next instruction can start 1 cycle after the previous one, entering the pipeline stages of the floating point unit, but it's going to take 3 cycles until the result has, for example, adding 2 floating point numbers has been produced. And of course, there is no way we can do forwarding or bypassing between these pipeline stages, sort of if you only produce, a third of the way to produce the result of the floating point, there's no way you can feed that information back to the next floating point instruction and expect that instruction could make any sense from it. So that is why we see these kind of restrictions on this architecture. We're going to look at a very simple example. In this example, we have a loop. We iterate 1,000 times, and all we do is go through all the elements of a vector, and we add some constant to all those elements. And the way a naive compiler would translate these kind of instruction would be a sequence of these 5 instructions here. So let's just try to understand what this mnemonic really means. So a register starting with an F, that's a floating point register. So this is floating point register 0. LD means load double, so that means it's actually going to load data from the address identified by this statement over here into 2 consecutive registers. So it's assumed that this architecture is a 32-bit architecture, but for when you do double precision floating points, you actually have to use 2 adjacent instructions to store the double data value. Add double, that means we are going to add the contents of 2 adjacent registers and another 2 adjacent registers together. So we here the register floating point 0 and 1, it's going to be, those 64 bits are going to be added together with the floating point register 2 and 3, those 64 bits, and the 64-bit result is going to be stored in floating point register 4. And also I should probably point out that the way this code is written, we assume that this vector here is actually stored backwards. So what I mean with that is that instead of incrementing I, we're actually going to subtract. Every time we go in this loop, we're going to make a subtraction of some value, and that the element x of I plus 1 is actually going to have an address which is lower than its predecessor in the vector chain. So here we're going to subtract 8 bytes because that's the size of the double of each entry of those vectors. So let's see exactly what's going on here. So first we do a low double. We store where we store the element of x sub I. So this R1 is pointing to the address of x sub I, and just for simplicity, we assume that this vector will actually end when R is equal to 0. Then we add the constant 10, and we assume that the constant 10 has already been loaded into register F2 by some of the prologue code that's not being shown here. So now we added 10 to the element x sub I in this statement. Then next statement we store the result back. So we store, this is where we identify the address, and we're going to store the value to, and then we take this value and we store into that memory location. Then we have to decrement this pointer pointing into the vector elements, and as already said, it's stored backwards. So we decrement by the size of a double. And then we see if R1 is equal to 0. If it's not equal to 0, then we're going to jump up to loop and do this all over again. So when you look at this kind of code and you try to figure out how fast it will, how many cycles it will take to execute this loop, you have to start to look for the data dependencies. And in this simpler kind of architecture, we always look for the read after write dependencies. So here we say we have a read after write dependence because this first statement is a write statement with respect to registers. We write a new value into floating point register 0, and that value is read here. So that's why we have read after write dependence between these two instructions. And we have another read after write dependence similarly between the add and the store double. So when we ask ourselves, how many cycles it would take to store the value, then we have to remember the specification of this architecture that says that there has to be at least one cycle between a load double and an add double, and it has to be at least 2 cycles between the add double and the store double, assuming now that there is these kind of dependencies here. So when we figure out how many cycles it takes to execute this loop, we have to take that into account. We also have to remember that we always execute the instruction following this branch because there was one delay slot. So calculating how many cycles it takes, we need to add a stall cycle here between the load and the add, and 2 stall cycles between the add and the store double, and then 1 extra stall cycle for the delay slot. So in total it takes 9 cycles to do 1 iteration of this loop where we have 5 instructions and 4 bubbles in the pipeline. Not a super good result. So the question is, can we reschedule instruction to avoid these stalls? Now we know what slows down the pipeline. And the tip on how to do this kind of reorganization is always a simple tip. Is always to try to take the loads and move them as high up as possible in the basic block, and move the stores as far down as possible in the basic block. So here, well, of course, this load we can't move any further up, but this store here we should try to move as far down as possible to pull the data dependencies as far away from each other as possible. So here again we have the original code with all the stalls, and following the advice, pulling the moving the stores as far down as possible, we're going to reschedule the instructions in this way. So we actually managed to put the store all the way at the end. The store is actually now in the delay slot after the branch. So that's very good. We already had the load at the very top. We couldn't put it any higher up. So we couldn't actually remove this data dependency we had at the beginning. But the effects of the second data dependency is completely gone. And now the branch delay slot is also used. That's good. There's one little peculiar thing going on here. If you look at the store said we're going to store the value to whatever R value is contained in R1 plus the constant 0. That's what we said over here. But to the right, we actually have changed this instruction. We say we're going to store the value to whatever R1 is pointing to plus the constant 8. So why the reason we're doing that is now when we move the store down, we moved it to the other side of the subtract. So when this store is executed, we already subtracted 8 from R1. So we sort of have to compensate for that by adding this extra constant, the 8 right here. Okay, so take a look at this. The very next slide, what I'm going to do is I'm going to ask you to do exactly the same kind of calculation, figuring out how many stalls that you will see in that code. So here you have a similar kind of loop 1,000 times. Instead of just adding a constant here to each vector elements, we add 2 vector elements together and put them in the elements of the first vector. And so this is what the kind of naive code that could be produced, where we load the element of xi, we load the element of yi, and here, of course, we need some other pointer pointing into that vector, so we're using R2 here. We add the newly loaded values together, and we store the value back to x sub I, we store the result. Then we have to subtract both pointers here to point to the next following item in vector x and y. So we subtract 8 from both of them. And then if R1 hasn't reached 0, we loop back again. So it's very, very similar to the code before. So the first question I'm going to ask is, so where are the read after write dependencies? Between which instructions in this code would you see read after write dependencies? So this is where they are. So the first 2 instructions, or the 2 loads, both have read after write dependencies pointing down to instruction number 3, the add, but to different registers. So there is a read after write dependence between I1 and I3, I2 and I3. Also, we have the same dependency between the add and the store as before. So we also have the dependence between I3 and I4. So the follow-up question is, how many cycles would it take to execute this, assuming that we do not optimize the code? And the answer here is 11 cycles. So just looking at the next slide, I showed you how this code would, how the stalls would be inserted in this code. And it's very similar actually to the previous example. There is no stall needed between instruction 1 and 2 because there is no read after write dependencies between those 2 instructions. But between 2 and 3, there is a read after write dependence. So we need the same stall here, and we need the same stall after instruction 3. And then when, of course, we have the stall in the branch delay slot as well. So we have 2 extra cycles here. So the answer is 9 sorry, the answer is 11 compared with 9 as we had before. So what we're doing with these kind of tricks here, compiler tricks, is we are improving the instruction level parallelism. Instruction level parallelism is a very important concept in computer architecture because by reorganizing the instructions, we can find a longer sequence of instructions that are independent of each other. So the reason we stalled in the pipeline was we didn't have enough independent instructions. And the compiler organization, really all it's doing is it's not writing a new application. It's just reorganizing the instructions to make sure that it becomes common that we have many instructions that don't depend on each other, adjacent to each other. That means that the pipeline now can work on more independent instructions at the same time. And even if you didn't think about it that way, the pipeline, it looks like a very sequential kind of structure working on a little bit of an instruction at a time. But actually inside the pipeline, you have some kind of parallelism. You are working on many instructions at the same time. And another way to say at the same time is to say in parallel. So with better scheduling of codes, you will be able to improve the ILP of your application. And the more independent instructions that your application has, the more independent things the architects will be able to do. And that will become even more important later on when we talk about more advanced pipelines. Last, in this video, we're just going to look at how if we can improve the scheduling of instructions even more by trying to apply the optimization across several iterations of the application. And this is something called loop unrolling. So here in this example, what I've taken here is not just one iteration of the loop, but 4 iterations of the loop. And I assume that there is some prologue code and there's some epilogue code after this loop that makes sure that when we get into the loop, we always have a number of iterations that we're going to perform, which is dividable by 4. So we know it's going to be in chunks of 4. We need to go in this loop. So here I took 4 iterations of the loop and I just put them right after each other, and I put all the needed stalls you have here in this loop. The reason you have the stalls is, of course, because you still have the same kind of data dependencies as before. So no improvement there, but there is an improvement at the end, because now we only need to do 1 sub I at the end, but instead of subtracting 8, we now need to subtract 32, because this applies to 4 iterations of the loop. Before we see if we need to go back to the beginning of the loop. Now, actually, we also managed to fill the delay slot with 1 store, because we have so many independent instructions going on here. So this is stored double down here, and there's, as you can see here, we have to manually decrement these accesses all the time here. And at the very bottom, because we go between I plus 1, I plus 2, and so on, without decrementing R1 in between. And then here at the bottom, of course, we should have had minus 32 as the constant, but here we have the subtract that actually has happened in between. So that's why we only have subtract 24 here at the bottom. If you optimize this code, we just apply the trick I told you about. We move the loads as high up as possible. We move the stores as far down as possible. And maybe we have to do some other smart organization. In this example here, we didn't need to do any more smart organizations. So here we have the 4 loads, followed by the 4 adds, followed by the 4 store double. And not very much else has changed in this code here. And but what we've done is we managed to pull the dependent instructions so far apart that we don't need to install any install cycles here. So both the load to the first add and add to the first store are now going to be 3 cycles apart. So that is cool. So the benefit here from loop unrolling are a couple of things. So it most of all provides a much larger sequential window of instructions that the compiler can work on. So the larger basic blocks we have, which is a sequence of instruction that contains no branches, the more freedom we give the compiler to be able to move instructions up and down. So this load here, for example, used to be way down before, and now we managed to move it way up here because the branch, the basic block is so large. So what you see here, if you count the number of instructions, first of all, it's a perfect scheduling of instructions. We eliminated all the stalls, so CPI equals to 1.0. We managed to do in just 14 instructions, which equals 14 cycles, we managed to do the work of 4 iterations. So now we're down to an average of 3.5 cycles per iteration compared with the 9 cycles we started with. So it's a speed up of more than a factor 2 compared with the original code. So this is quite impressive.